want to do something differently today. I really want to go slow. So I really want to make sure that everybody understands every detail, and I'm going to use up the entire time just solving those, just one question. Okay? So you know how detailed I want to go, right? Okay? So I will try to explain, but then I'll re-explain and I'll elaborate, and whatever you need to do in order to understand, I'll do it. Okay? All right. So let me start by writing down the equation I want to solve. Ut equals to 3uxx, and ux 0t equals to ux 7t equals to 0. And then ux 0 equals to 2x plus 1. And I already explained what heat equation is, why the second derivative, the concavity, will control how fast the temperature will go up or down. That's what this equation is saying. And I already explained that this one is the initial condition because that's the shape of the temperature at time t equals to 0. By the way, here u is a function of x and t, and it's the temperature at time t at location x. That's what it means. All right. What's different today is that in the previous lecture I solved this one where you didn't have this subscript x. Now this subscript means partial derivative. So if I actually write this down, it means that the derivative of u with respect to x would be 0 if you evaluate at 0, okay, for all time t. So that's what this means. And such a condition is called a Neumann boundary condition, and I didn't explicitly say the other condition, but the previous condition I had, which was like u of 0t equals to 0, and u of 10t equals to 0, these are called Dirichlet boundary conditions. Now, this one is easy to understand because that just means that your temperature at the endpoints are fixed to 0 because it's touching something cold. Say something like ice is touching it. Now, this is a bit harder to understand, and I'll just tell you right off the bat that this means that the endpoint is insulated. So, in other words, we're thinking of a very thin rod of length 7, 0 through 7, and it's insulated all around, not only just the radial direction, but also the endpoints. If that happens, you call this Neumann boundary condition. And let me explain why by first thinking about what's going to happen as you make the temperature do its evolution according to the heat equation. So here's the shape of the initial temperature distribution at time t equal to 0. Now I'm assuming that the rod is 7 meters long, so you have 0 through 7. And when you plug in 0 to this, you get 1. And when you plug in 7 here, 7 times 2 is 14, 14 plus 1, that's 15. So you end up with a straight line connecting the two. And then now you have to think about what will happen as time goes on. So if this is what it is and it's insulated completely around it, then what's going to happen at this endpoint is that because for this point it has a lower temperature on the left side but there's nothing else, this is going to go down, right? Same thing here. This one has higher temperature on this side, so heat will flow to this direction, so it's going to go up. Okay? However, in the middle, you have heat coming in and you're losing heat, so they just cancel. So in the beginning, you're only going to have, you're not going to see any change in the middle. You're only going to see a curve that looks like something like this. Okay. So that would be our the temperature distribution shortly after time t, shortly after 0. And then as time goes on for a longer time, then you get more and more, and then eventually it's going to average out, right? So everything will become uniform. That's what you'll see. Okay? Now, once you see how it should evolve, then you can see for yourselves that as this comes down, you're going to have a temperature distribution that's like this, where at the endpoints you have a horizontal slope, right? Can you imagine that? As this thing goes down and this thing goes up, your temperature at the endpoints will be like horizontal. And that's exactly what this means, because if the derivative is equal to 0, what does that mean? That means the tangent line is flat. It's horizontal, right? So it just is a condition to describe what's happening at the endpoints. Okay. So another way to say it is like there's no heat going through the endpoints. That's how people try to describe this. But rather than saying it that way, I think it's easier if you just imagine how the heat is going to do its evolution with respect to time. Then it's kind of obvious that this is the condition to describe when you have insulation all around. Okay? So that's called Neumann boundary condition. This is called Dirichlet, and this is the one that I'm trying to solve today. Yes.
So eventually, would it just become flat all the way? So it'd be like
yes,
okay.
Yes. So that's another thing that we will do at the end. So after we solve this, we'll try to look at the steady state solution, which is like what happens to the solution when time t goes to infinity. And you'll see that you actually get a flat function at the end, a constant function at the end. Okay. All right. So let's actually solve it. Okay. As I promised, we're going to go slow. So I really need you to remember these steps for me. Okay. So step 1. How do you start solving such a question? What do we do? Uh-oh.
Find the solutions of the equations with the boundary conditions.
Yeah, so you only solve for the first two. And this is like the initial condition, so we can add that later. So what we're trying to do is we're trying to find the building blocks for the general solution of this equation. So we forget the initial condition for a moment, and then just solve the heat equation and the boundary conditions, and then that's going to give you the general solution. Right? So that's the first approach. So we find all solutions to the heat equation and the boundary conditions. Okay. In the form of what form? Does anyone remember? Yes.
Is it x of x?
Yes, yes.
Times 2t?
Yeah, you think of it as a function of x, function of t. You're just trying to find the building blocks. So this is what we call the ansatz. We're trying to guess the solution. If we make a successful guess, then our existence and uniqueness theorems for the heat equation will tell us that we did find the correct answer. So it's okay to guess the solution when it comes to heat equation. Okay. All right. So we're trying to look for solutions that look like a function of x times function of t. I could very well have named this as f of x and g of t, but then sometimes you forget which one's which, so I just named it conveniently as the capital X for the function of x only, capital T for the function of t only. Okay. So what is this approach called? What's this method called? Method of, yeah? Separation of variables. Yeah, you've separated the x and separated the t. Okay. All right. So we're trying to find this type of solution, and the story goes that you plug it in and you look for all the solutions, and what you'll find that you get infinitely many solutions of this form. If you have many solutions, what do? Yeah.
Pick the simplest.
No.
Oh, no. Oh.
If you have many solutions of this, what would you do? You get the summation. Yes. It's called the linear combination. Right? You add up all the solutions and you get a big general solution. And then after that, once you get the general solution, you can plug in the initial value to figure out what the values of the coefficients are, like C0, C1, C2. You have infinitely many, but you can find it. Okay. So that's the idea, all right? So let's actually try to plug this in. So if you plug this into the left side, ut, remember this subscript t means you're differentiating by t. What would you get if you differentiate this by t? It's a partial derivative, so how does it treat x of x? It's a constant, so you're only differentiating this, right? So what would you write?
X of x. T prime.
T prime of t, yes. Okay, on the right side you have 3. And now what? You're differentiating x only, right? It's a partial derivative of x, but this time twice, right? So you do x double prime. Okay, so that's what you get. There's this next step that you have to memorize. What should we divide both sides by? Yes?
Is it 3x?
Yes, 3xt. 3xt. Where I should really be writing x of x, but just for simplicity. This is really x of x and that's t of t. And if you divide this by this, I see that they both have x of x. So these two will cancel. But t prime and t, although they look alike, they're different functions, so you can't cancel them. So that makes the left side as t prime of t over 3t of t. Okay, so think about what you will get on the right side if you divide by 3xt. What cancels and what's still left?
T of t cancels.
Yeah, t of t cancels.
So you have x.
Double prime stays.
X double prime of x over x of x. Okay. And then there's this crucial argument that we make. The left side is a function of t. The right side is a function of x. But this equal sign in differential equations is always equality of functions, right? So you're saying that a function of t is same as a function of x. Sounds ridiculous, but it can be done only if when?
They're constant functions.
When they're constant functions, right? We talked about this for a long time last time. So the only way you can have a function of t equal to a function of x is when they're both equal to a constant function. In other words, they don't depend on t nor x. So now we have to set it equal to some constant, and that this is another thing to remember. You actually have to name that constant as what? We decide to name it as negative lambda. Now, I could name this as, rather than negative lambda, I could name it as just A or B or whatever letter you like. But I'm just saying that naming it as negative lambda will make it, turn that into a form that we've solved before. So that makes it easier to solve. Same thing over here. You can just, instead of divide by 3xt, you can also divide by 3 and still make the same kind of argument. But those small choices, if you make the different choice, then you end up with a messier kind of question to solve. So just to make your calculations a bit easier, you want to memorize that you always want to divide by kxt. And you also always want to name your constant as negative lambda. That's what you want to do, right? Okay, let's continue. Now this is, how many equations is this? How many equations is this? It's actually two equations, right? It's this one equals to negative lambda, t prime over 3t. I'll not write parenthesis t. This is really t prime parenthesis t. It's a function of t. I'm just suppressing the parameter. Hopefully you understand. Okay, and then that's equal to negative lambda. And if I multiply 3t both sides, then this 3t will cancel out. And that's going to give you t prime equals to negative 3 lambda t. Is that good? Right. Okay, and then x double prime over x equals to negative lambda will be the other equation, right? This equals to this, and this also equals to this. And that one, if you solve by multiplying by x both sides, you get x double prime equals to negative lambda x. And then you add negative lambda x both sides, and you get x double prime plus lambda x equal to 0. So you get two solutions, two equations, right? You get one equation here, you get another equation here. Okay, so let's stop here. That's how much we can extract by plugging this ansatz into the very first heat equation. Now let's try to see what happens if we plug it into, can you put the camera to this way? Okay. So what I'm trying to say is that if I plug this into the first one, that's what we get. And if I plug that into the second line, then we get another condition. Okay. So let me write it over here. So the condition over there was ux 0t equals to 0. And remember, u of xt is x of x, t of t. And therefore, if I differentiate by x, what do you get? What should I write?
0t
X prime and t of t, right? But then I want to plug in 0 and t, so it will be x0 t, right? The other condition was that this ux of 7t equals to 0, and that one is going to change to, oh, by the way, this is equal to 0, right? So that's one condition. And this condition translates to x prime of 7 times t of t equals to 0. So we have these two conditions. And whenever you have product of two things, that means one of them has to be 0, right? So it's either x prime of 0 equals to 0 or t of t equals to 0. However, we don't like one of them. Which one?
T of t equals to 0.
We don't want t of t to be 0. Why?
Because then it's trivial.
Because then u of xt will be just 0, right? So we say t of t cannot be 0 because if t of t is 0, then uxt, which is the product of x of x and t of t, is just going to be 0 as a constant function, and that's called a trivial solution, right? It doesn't add to our vocabulary of solutions. We want to find all the solutions, and these are the ones that we already know to be solutions, right? A 0 will satisfy the heat equation no matter what, and these boundary conditions will also be satisfied by a 0, so that really isn't what we're looking for, okay? So we're really looking for non-trivial solutions that look like this. So that's why t of t cannot be 0. And that means that we are going to have instead x prime of 0 to be 0 and x prime of 7 to be 0. So we are forced to have this. Okay, that's our conclusion from the boundary conditions. Okay? All right, so now let's take this boundary conditions with the equation for x that we observed, this was the equation that we got. And let's try to solve this. Well, we actually solved this before, right? Do you remember the solution? This is, we know that the solutions look like cosine n pi over 7x with lambda being n squared pi squared over 49 with n equals to 0, 1, 2, 3. So that's something that we got. And I think we should do this again. What do you think? Do you want to see how it's done again? Okay, so we'll do that. But before I do that, let me just ask: is there any part that we've done so far that you did not understand? Okay, were you clearly following everything? That's good. Should I explain anything one more time? You think you got everything? Okay, great. So then let's try to see why this result is true. So, this solution. First, you want to write down the characteristic equation. So r squared plus lambda equals to 0. Because x double prime corresponds to r squared. X is just 1. So that's what you get. And then you solve this. R squared is negative lambda. And then if you solve for this, it's plus or minus square root of lambda I, where I is the square root of negative 1. So that appears, right? So that's what we're going to get. And that means that the solution looks like x. Well, let me write it up there. Solution looks like x of x equals to c1 times cosine square root of lambda x plus c2 times sine square root of lambda x. Now we apply the bound. Oh, to apply these boundary conditions, I need to differentiate. So let's differentiate once. So you differentiate, you get negative c1 times square root of lambda sine square root of lambda x plus c2 times square root of lambda times cosine square root of lambda times x. And then let's apply the very first condition, which is x prime of 0 equals to 0. That makes it as, if I plug in 0 here, I get 0 on the left side, but on the right side, what sign of 0?
0.
So this is, sine 0 is 0, so that doesn't appear at all. What's cosine 0? 1. So you're going to get c2 times square root of lambda. Okay. Once again, I have a product of two things equal to 0, right? If two things multiply to 0, then we know that at least one of them is 0, okay? And let me ask, can lambda be 0?
No.
Why not?
Make it a trivial solution.
No, that's not the answer this time. Okay, so lambda cannot be 0, but for a different reason. This time, I actually kind of sneaked in some additional assumption here when I went from here to there, because, you know, if lambda is 0 here, what happens? Then you get a double root, 0 and 0, right? R squared equal to 0 has one single solution, which is a double root, 0 and 0, okay? So you wouldn't be getting this solution when lambda is 0 because it doesn't have an I. You get a totally different kind of solution. Only when lambda is positive, you're going to get this solution. So what's really happening here is here, I'm assuming that lambda is positive, okay? So we're doing the case when lambda is positive. If lambda is indeed positive, then we can go ahead and say this, and because lambda is positive, this cannot be 0, so you're forced to have c2 equal to 0, because lambda is positive. Okay. Now that we have c2 as 0, this no longer exists, then x prime is just this much. That goes away, and it's just this much. Now let's plug in 7. And if I plug in 7 into x, x prime of 7 is 0. So x prime of 7 is 0. That makes 0 equals to negative c1 square root of lambda times sine square root of lambda times 7. Okay. Now you have 3 things multiplied to 0. So we have to figure out what happens when each of these are 0. Okay. So can c1 be 0? Why not?
Then you got a trivial solution.
Then you have a trivial solution. Yes, because x is this, and we already know that c2 is 0. So x is just this much, but if c1 is also 0, then you have a trivial solution. That's not the solutions we're looking for. Trivial solutions are excluded. So c1 cannot be 0. And we already know that lambda is positive, so that cannot be 0. So that leaves the sine of square root of lambda times 7 being 0. But when can this happen? When can sine functions become 0? Integer multiples of pi, right? Sine is 0 at sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine n pi is 0. So we know that square root of lambda times 7 must be equal to n pi. And then you divide both sides by 7, which gives you that square root of lambda must be n pi over 7, which is nice because now we have the solution there, right? So we already have that x of x must be c1 times cosine of n pi over 7x. And we just need to have one solution. So the thing is, if we find the t of t will also come with some constant in front. So you have some arbitrary constant here and arbitrary constant in t of t. And they multiply together, so they just make up another random number. So we actually don't need this c1 because we're going to put the u as this times the t of t, and t of t already has a coefficient in front. So I'm just going to get rid of this, and it's also in accordance with the fact that when we look for eigenfunctions, we just need one function because there are many different non-trivial eigenfunctions. And they're multiples of each other, so we just find one of them, okay? And then lambda would be, now for lambda itself, you have to square both sides, and the result is that you get n squared pi squared over 7 squared, which is 49. And n would start from 1, 2, 3, and so on, so on, okay? Okay. But that's not everything. We also have to check for what? We have to check for the other case. We did the case when lambda is bigger than 0, right? So which case should we do?
Plus 0.
So we also have to check for the 0 or the negative, but as I explained, these type of operators, the negative, if I move this to the other side, it's negative second derivative. That's one of the Sturm-Liouville operators. And those never have negative eigenvalues. So the only thing that we have to check is what happens when lambda is 0. Okay? I don't have any room, but let me just write it tiny here. When lambda is 0, then what happens is that r would be a double root, 0 and 0. Right? So that your solution would look like e to the 0x for one of them and another e to the 0x, but they have to be different. So what do we do with the second one? We multiply on x, right? So here's c1 and here's c2. And anything to 0 power is 1, so you get the solution c1 plus c2x. So that's one way to get it, but you know, you kind of already see why that should be the solution, because if lambda is 0, what's our equation? It's x double prime plus lambda x equals to 0. So if lambda is 0, you just get x double prime equal to 0. But what function gives you 0 when you differentiate twice? Ax plus b. That's exactly this one, ax plus b, right? So if you know this, I mean, if you're doing this on an exam, if you know that, you don't have to write all this, and you can just say lambda equal to 0 should be ax plus b. It'll save you some time. So if you understand more, then you can save yourself writing some stuff, okay? So I'm totally fine with that because that's kind of obvious. Now let's plug in the endpoints. So I need to differentiate. The derivative is C2 only. C1 its derivative is 0. C2x differentiates to C2. And therefore, the two boundary conditions that x prime of 0 equals to 0 and x prime of 7 equals to 0 will both just turn into saying that C2 is 0. In other words, if C2 is 0, then it's going to satisfy the boundary conditions. But what does that mean? If C2 is 0, then x of x is just C1. Now here's a question. If I have a constant function, so this is my answer, it's C1, is that a non-trivial solution? Yeah, I mean, the word trivial means very easy, so it kind of seems easy, but in our definition, in the math definition, in this context, we will only say a solution is trivial if it's completely 0, okay? So if this is anything other than 0, this is a non-trivial solution, okay? So that we're going to write down the solution as any non-trivial, non-zero number, and among them the simplest one is 1, right? So I'll just choose the one eigenfunction as 1. Okay. Then, what does that tell us about lambda equal to 0? If a lambda value allows for a non-trivial solution, we call the lambda value as eigenvalue. Yes, it's called an eigenvalue, right? So lambda equal to 0 is an eigenvalue. Sorry, cramped space. Lambda equal to 0 is an eigenvalue. So that's the case when lambda is 0, and we don't have to do the case when lambda is negative. And when it comes to writing this answer, this will be actually important for many of you, because if you write it in the wrong way, you get 1 point taken off. And because so many people in this class are getting 90s, and it's a very good class, I think that 1 point is going to hurt. So please pay attention to what I mean. Okay. So when you write your answer, you should write this as your answer. You want to say that the eigenfunctions are cosine n pi over 7x, and the eigenvalues are n squared pi squared over 49. But you have to put 0 in there. Okay. Now let's see why 0 is now included. Before I had n equals to 1, 2, 3, but n equals to 0 should be included. And missing that 0 will be costing you 1 point on the exam. So make sure that you write this, okay? Now let's see why 0 makes sense. If n is 0, what's the value of lambda? 0, okay? When n is 0, what's the value? What's the function x of x? 1. That's exactly this case, right? When lambda is 0, your eigenfunction is 1. So just putting a 0 will automatically include the lambda equal to 0 case, which saves you a lot of writing. Okay? So that's how we're going to write. Okay? And make sure you don't forget this 0. And then, so that's how I got this answer. Okay? And as you can see, in this answer I said n starts from 0. That's the whole thing. Yes?
And is every case n equal to 0 or no?
So I think the question is like, would n equals to 0 always be included as the eigenvalue? And the answer is no. In the Dirichlet boundary conditions, you'll find that the solutions will like sine functions. And if it's sine of n pi over 7x, and when you plug in 0 into there, you get a 0, which is a trivial function, right?
Okay.
So for that case, n would start from 1.
Okay.
Okay, so if the boundary condition didn't have the primes, then the solution will be sine function instead, and it'll start from 1.
Okay.
And that's something nice to know. Even if you didn't solve it, you would kind of have some expectation of what kind of functions you will have, right?
Yeah.
So although I gave you this formal solution, actually, it's a good thing to have some intuition behind what the solution might be. Now, you may have noticed that I do all this without any notes, and because if you do this for a long time, it's kind of obvious what the solution should be. So let me share you my insights here. So look at the cosine functions. So a cosine function looks like the following. It looks like 1 and then 0, and then negative 1 and then 0 and then up. Right? So that's a cosine function. And in one period, what do you see about the endpoints? What's special about these endpoints?
Horizontal.
It has a horizontal tangent line, right? So the derivatives will be 0 at the endpoints. Okay? Right. Now, just to give you an idea of what these functions look like, think about what happens when n is 1. If n is 1, you get x of x as cosine pi over 7x, with this being like the angular frequency, right? Now, who can tell me the formula for the period if you know the angular frequency? How do you get the period from angular frequency? Huh?
Isn't it 2 pi over w?
Yes, it's 2 pi over, it's not w, it's omega, okay? So omega, it looks like w, but it's supposed to be the Greek letter omega. All right, so it's 2 pi over omega, and in our case, it's 2 pi over 7, and dividing by a fraction is multiplying by its reciprocal, so it's 7 over pi, then pi cancels, and you get 14. Right? So what's happening is that this graph has this has one full period. Right? But remember, what's our bar length? What's the thin rod's length here? 7. So it's actually right here. So it's not the full thing that you have, but actually it's just this half that you're drawing. Okay, that's our x of x when n is 1, and so you have to check whether the endpoint conditions are satisfied. How are they? Is the derivative 0?
Yes.
How about here? Is the derivative 0? It is, right? So indeed you get 0 derivative in both cases, and then you can see that if you increase the angular frequency further, then you get something like some highly high frequency cosine function, and then if it's even numbers, then it's going to both end up at positive 1, and if it's odd, it's going to end up at negative 1. But anyways, if you look at what's happening at 0 and then 7, then you'll see that you always have the derivative equal to 0. That's how I remember to put the cosine function when you have prime. Okay. On the other hand, if you have the sine function goes like that, so it has 0 at the endpoints, and that's the function I will write down when there is no prime, if the value of the function is 0. Okay. And just having that in your head will immediately tell you what to do. Okay. And it also helps with the fact that when you think about the Fourier cosine series, the formulas are like cosine n pi over L, x where L is the length of the interval, and that coincides with the bar length at this point. So that's another way to remember how things are related. And I mean, if you actually do the solution afterward, you'll see that you actually want to represent some initial condition as the Fourier series of these things. So that's why it makes sense. Okay. All right. So let me give you some tips about the exam 3. In exam 3, I will have several parts, and this will be like question 1. This one will be like this question right here. Find all the eigenvalues, eigenfunctions. That will be question 1. And then you will have to do all the work that I've raised, which is like assume that lambda is positive, and this, and then lambda is 0, then this happens, and then you don't have to do the lambda negative case, but at the end of the day, this should be your answer. That will be question and answer for question 1, right? Now, question 2, you're going to get a question about Fourier cosine series, which we are going to do later. Okay? And the question will be 15 points. Question 2 will be 15 points, right? And then when you solve this heat equation that we're solving right now, then you can include those first two parts as, because you've already solved that as question 1 and 2, right? And that'll be like 20 points. So already you have like 20 plus 15 plus 15, that's like half the exam. Okay? And there are some other questions regarding some other Fourier series, but so that's what's going to happen on your exam. Okay, is that good? All right. Okay, so let's proceed. Okay, where were we? We kind of got caught up with this one. So once you accept that that's the solution, now we have to go back and see what it implies. So let me erase this. Let me come back over here. So we had two sets of equations from the heat equation, right? And we also got boundary condition for this and ended up with x being cosine n pi over 7 x, and also lambda has to be one of these numbers. Only when lambda is one of these numbers, with n equals to 0, 1, 2, and so on, you're going to get non-trivial solutions. For any other lambda values, this is not going to give you any non-trivial solutions. It will only give you 0 as the solution. So these are the values that we can expect a non-trivial solution. And that's just this side. Now we have to solve this one. Let's try to solve this. T prime equals to negative 3 lambda t. I say that the solution looks like e to the negative 3 lambda t times c. This has this solution. Okay. How do we get that? I didn't explain it last time. I just said, oh, this is the solution. First, how would we check this? Just differentiate, right? Yeah. So how would you do it? Just think of it like this. If t is e to the negative 3 lambda t, what is t prime? Well, the chain rule says this comes in front, right? So you have negative 3 lambda, e to the negative 3 lambda t. Right? But we decided that this is t, right? So that's indeed equals to negative 3 lambda t. So we see that if I plug this into the left side, it's same as the right side. So that is indeed a solution. And if that's a solution, and this is like a linear homogeneous differential equation, so any constant multiple is a solution. So that's how I know it's a solution. Okay, so that will be how we guess the solution, which is perfectly fine. It's the first order differential equation. You have a solution with one free parameter, which does work. So we found all those solutions by existence and uniqueness of differential equations. But let me ask another question. How would we actually solve it? Here's how we think of it. We can move this to the other side, and we get t prime plus 3 lambda t equal to 0. What kind of differential equation is this? First order, and it's linear. It's even homogeneous, but all we need to know is that this is a first order linear differential equation. How do we solve a first order linear differential equation? Find the multiplier, right? E, integrate. Now the independent variable is t, so a lot of times we said px dx, but here we're going to integrate by t. And pt is whatever that's in front of the dependent function, so pt will be a constant, 3 lambda. So we have e to the integral of 3 lambda dt, which gives you e to the 3 lambda t. Okay, and then what do you do with the multiplier?
Multiply it.
Yeah, it's called a multiplier because you multiply. So you multiply. And then magically, the left side turns into product rule, right? So you get 3 lambda, no, not that 3 lambda, e to the 3 lambda t of this function t of t prime equals to 0. And over here, am I in the camera? Okay, thank you. So if you integrate this both sides, then you end up with e to the 3 lambda t times t equals a constant, so that t would be c over e to the 3 lambda t by dividing, but then exponents in the denominator can be moved up by putting a negative exponent. And there you go. Okay, so that's how you get this solution that I wrote before. But you know, this is so basic. When you write this on the exam, if you go straight from here to there, I'll be okay. I think this is not something that you really have to solve like this. So you know, if a function's derivative is some constant times itself, then it must be e to some power. That's how you remember. Okay. Yeah. All right. So that's what we have, and then you multiply the two functions that we obtained. So u of xt, as we agreed, it's a function of x times function of t, and we actually found the two functions. First, t was this thing, it was c times e to the negative 3 lambda t, and then x of x was cosine n pi over 7x. And that is the result of our step 1. We decided to look for any solution that looks like a function of x times function of t that would solve the heat equation and the boundary conditions in general. And we got this. These are the only ones, okay? Those are the only type of solution. Oh, sorry, I missed an important point here. We also got lambda as n squared pi squared over 49, right? So that should have been plugged in here. So sorry about that. 3n squared pi squared t, and then divide by 49, and cosine n pi over 7x. Okay, that's step 1. Okay. All right. Once again, I invite you to ask me any questions that you have. Do you want me to explain anything again? You fine with so far? Okay. I found what x was. It's this one. I found what t is. It's this one. So this product is the only type of non-trivial solutions that will satisfy the heat equation and the boundary condition. Yes.
What do you do about C?
What do you do? What?
What do you do about it? How do you solve for it?
Oh no. So the question is, what do we do about C? Well, so right now we don't have the solution for the initial condition. This is not met. This was our initial condition, and there's no way if you plug in t equal to 0 here, you're going to get 2x plus 1, right? So that's not possible. But there's one more step that you have to think about. If we have these solutions, how many solutions do we get? N is from 0, 1, 2, 3, right? So how many solutions are there? Infinitely many, okay. What do we do with those, if we have those infinitely many solutions? We add them up, right? See, if independently these are solutions, then the boundary conditions and the heat equations are such that any sum of two solutions is again a solution. It satisfies this linearity property. So if you have these solutions, you can add them up and there will still be a solution. So what you get out of the step 1 is the following very important conclusion, that uxt is sum of all these, summation of n. Well, let's write that first. C, I'm going to put Cn there because you can have different coefficients for each of these building blocks. Cn e to the negative 3 n squared pi squared over 49 times t cosine n pi over 7x. And n starts from where?
0.
0, thank you. And start from 0, and you go up to infinity. Okay. And this is the general solution. Well, we actually don't know. Maybe there are some other solutions that cannot be expressed like this, but we don't care. As long as we can make this somehow satisfy the initial condition, then we're all good. Actually, you can show that you can indeed take any solution and any initial condition and turn it into this form through what we call the Fourier cosine series. Okay. All right. So let's go back here and no, let me just erase a whole lot here. And now let's start with step 2. I'm going to write down the result of step 1, and we will proceed to step 2. From step 1, we know that these two have the solution uxt equal to summation of n equals to 1 through infinity of Cn e to the negative 3n squared pi squared over 49t cosine n pi over 7x. Okay. Now let's see what happens to the initial condition. You're plugging 0 into t, right? So you have u x0 equals to summation n equals to 1 through infinity of Cn. Now what do you get if you plug in 0 here? It's just 1, right? E to the 0th power. So that we don't have to write. So that's just 1. So you just get cosine n pi over 7x. And because u of x of 0 is 2x plus 1, you get the following. Okay, so that's what we're getting. And then, oh, sorry, this should have been from 0, right? That's a fine detail, but that could lead to a disaster, sorry. Okay, so it should start from 0, okay? All right, so in order to transform this into this form, to get what Cn is, we have to use the following Fourier cosine series. So let me write down the Fourier cosine series. Fourier cosine series formula. And it goes like this. You have an given by 2 over L integral from 0 to L of f of x times cosine n pi over Lx dx. And that's how you get the coefficients an. And we're assuming that the function f of x is any function that's defined from 0 to L. Okay? Then once you get these ans, then you can say that f of x must equal to a0 over 2 plus summation of n from 1 through infinity of an cosine n pi over Lx. Okay. So these two are the formulas for the Fourier cosine series. You can have any function defined from 0 to L, then after getting your an and putting into this series form, you'll see that these two functions are equal over the interval 0 to L, except that there might be a few single points that doesn't agree, but the two sides will mostly be equal. And if the function itself is a continuous function, then at least in the inside of 0 to L, they're going to be equal. Okay, anyways, so that's the formula for the Fourier series. Let's apply it to our case. And you have to remember that although I'm writing just a single formula, this is actually two different formulas, right? How is this single thing a two different formula?
One gives you the coefficients of the series. The other.
Okay. Yeah.
Because you have to do A of n and A of 0.
Yeah, because you have to calculate a of 0 separately from an. Okay? See, when n is 0, this cosine 0 just becomes 1, right? So you get a completely different type of integral when n is 0 compared to the other. If n is not 0, then you get a cosine function and you have this 2x plus 1, so you will have to do tabular integration. But if n is 0, you don't have a cosine function, and the way you integrate is totally different. You just have to integrate 2x plus 1. So remember, even if it looks like I wrote a single formula, it's really two formulas written as one. Okay? You have to calculate the n equals to 0 separately. So a of 0 is 2 over, RL is 7, right? So 7, integral from 0 to 7 of 2x plus 1, and just dx. And then that one is 2 over 7, x squared plus x, and you have to plug 7 and 0 here. 7 squared is 49, 49 plus 7 is 56, 56 divided by 7 is 8, 8 times 2 is 16. So you get 16. And then when n is greater than 0, then you get an as 2 over 7 of integral of 0 through 7 of 2x plus 1 cosine n pi over 7 x dx. And this one we have to use the tabular integration. So let's put the plus minus d integral 2x plus 1, 2 and then 0. You have cosine n pi over 7x. The integral is 7 over n pi sine n pi over 7x. And I'm doing this a bit fast because it's so straightforward, and we have been doing the Fourier series before, right? So every time you integrate, the reciprocal of this number comes in front. Sine integrates to negative cosine. And another 7 over n pi will make this 49 over n squared pi squared. Cosine n pi over 7. And you have plus, minus, and plus. And then you have to multiply like this and like that. So the result is that you have 2 over 7. And you get 2x plus 1, 7 over n pi, sine n pi over 7. Sorry, there should be x here, n pi over 7x. Okay. Plus 2 times 49 is 98, n squared pi squared, cosine n pi over 7x. And then we have to plug in 7 and 0. Okay. Let's plug in 7. If you plug in 7 here, you get sine of n pi over 7 times 7. 7, 7 cancels. What do you get?
0, 0.
Yeah, you get sine n pi, which is 0. So you're going to get 0 when you plug in 7 here. If you plug in 7 here, what do you get? Cosine n pi. What's cosine n pi?
-1.
Negative 1 to the nth power, right? Cosine alternates between 1 and negative 1 if you evaluate it at integer multiples of pi. So because it alternates, it behaves like negative 1 to the nth power. Okay, now minus, let's plug in 0. What do you get? What sign of 0?
0.
0. So I don't have to write anything, it's 0. Okay. How about this one? We plug in 0. What's cosine 0?
1.
So we get
Minus.
98 over n squared pi squared. And since it's a little bit messy, let me erase this one and write down the result. If you divide 98 by 7 and multiply by 2, you're going to get 28. And since 28 over n squared pi squared is a common factor, if I factor that out, here's what we get. We get negative 1 to the nth power minus 1 as my an. Okay? All right. So now that we have the ANs, let's see what we get if I plug them into this formula. So f of x is 2x plus 1, right? A0 is 16 over 2, right, which is 8. And then this one is summation n from 1 through infinity of 28 over n squared pi squared of negative 1 to the nth power minus 1 cosine n pi over 7x. So that one we erase. Okay, so that's what identity we succeeded in getting by using the cosine formula. And now if you compare this with what we want, they look very similar, right? Except that the one thing I don't like about this one is that this starts at n equals to 1. This one starts at n equals to 0. So we have to think about what happens if n is 0. If you plug in n equals to 0, what happens here? What's cosine 0?
1.
So you just get what?
C.
C0, right? So you can rewrite, I can rewrite that as 2x plus 1 equals to C0 separately plus sigma, now n starts from 1 through infinity, as Cn cosine n pi over 7x. Right? This summation is essentially same as this one because you're just taking out the case when n is 0, then afterwards n goes from 1, 2, 3, 4, 5 to infinity, so the rest of the sum is this one. All I'm doing is I'm just writing the first one as a separate thing. Is that good? Okay. All right, so since I'm almost out of time, I guess I'll have to keep going. All right, so here, by comparing these two, what do we get as the value for C0? 8. What do you get for Cn? These two are the same, these two are the same, so this part must be same as Cn, right? So this entire thing must be Cn. So we write 28 over n squared pi squared of negative 1 to the nth power minus 1. Okay, so we got the C0, we got the Cn's for n1 to infinity. And that's great because we almost have the solution, right? And all we need to know are the Cn's, and we found the Cn's. So all it's remaining is just the answer. All right, so what is the answer? Answer. I can write down the answer for the entire question, okay? So it was a bit long journey, but we're almost at the end of it, okay? All right, so the answer is that uxt is, if you set n equals to 0, same thing happens here. If n is 0, this is just 1, that's also 1. Because you have n here, you get e to the 0th power, which is 1, cosine 0 is 1. So when n is 0, you just get C0 as a separate thing. So C0 plus summation from 1 through infinity of Cn e to the negative 3 n squared pi squared over 49t cosine n pi over 7x. And now you just plug in the coefficients and you get, actually, so the actual answer is this one. Uxt would then be 8 plus summation n equals to 1 through infinity of 28 over n squared pi squared, negative 1 to the nth power minus 1, e to the negative 3 n squared pi squared over 49t, cosine n pi over 7x. So that's the final answer. Okay. All right. Although this was a long problem, let me finally put one more thing, because this will be like a 5-point question on the exam. Okay. So this will be part A, and part B, I'm going to ask, what is the steady state solution? What is the steady state solution? Okay, so tell me what steady state means. Yep.
I'm just gonna guess, but is it when there's not really much in the way of change?
Right. And when would that happen?
When you have known constants, so you use your
Okay.
When it's
I agree with that, but any other answer? Yes.
when the
Time equals infinity?
When time is infinite. When you see, we talked about the evolution of this thing. Initially, you have 1 here and 15 there, and you have this straight line, and then the solutions will evolve like that, right? And eventually, it will be a flat curve. It will be a constant function. Okay. What function would it converge to? Do you have any idea? Why 8? Yeah, it's 1 plus 15, 16 divided by 2. You must have 8 as the average, right? Yeah. So that's our intuition, right? And that better agree with this solution. So how do you get this? You just say limit of t going to, oh, let me write it somewhere else, because this is going to be 5 points, right? So let me write here. So we want limit, the steady state solution is limit when t goes to infinity of uxt. But since u is this thing, and if you look at this, the only place that has t is right here. Okay, so we can bring the limit to just here. Okay. Now there is actually one fine point that if you have an infinite sum, switching the limit and the infinity is a bad idea sometimes. You get totally wrong conclusions here, and there should be some mathematical justifications for it, but that's outside our curriculum. So I'll just say we can't. Okay, so if we do, here's what we know. This should be equal to 8 plus summation n from 1 through infinity of 28 over n squared pi squared, negative 1 to the nth power minus 1, limit of t going to infinity of, am I still in the camera? Okay, thank you. So you have e to the negative 3n squared pi squared t over 49, and then cosine n pi over 7x. And you have this part. So what do you get? You get e to the negative infinity, right? What is e to the negative infinity?
0.
Yeah. E to the negative infinity is 1 over e to the infinity, and e is 2.7, so if you take infinite powers of it, you get a very large number, right? So you get 0. So what's happening? This will be 0, right? So all of these terms will be 0, and what are you left with?
8.
8. So that's what you have to write for 5 points, okay? Pretty easy, right? Yeah.
Can you just write 8?
Huh?
Just immediately go.
Oh, then you
up
have to write this limit.
Ah.
Okay. You have to say that. Okay. Yeah. Then I give you 5 points. Okay. All right. So that actually is pretty nice because it does agree with our intuition, and so you can be more confident that this is what it is. Now, if I had the time, I could also draw this on the Python and show you how it actually gives you this, but we don't have the time, so that's all for today.